transformation to the given differential equation, and we have the Laplace transformation formulas for the derivatives. So we have here a third order derivative, and when you take the Laplace transformation for third order derivative, we can have the formula like s power 3 into y of s minus s square y of 0, s into y dash of 0, and so on. Here this s is a frequency variable, and values of first and second order derivatives are taken at the point t equals to 0. Similarly, in case of second order derivative, the Laplace transformation formula goes like a s square into y of s minus s into y of 0 minus y dash of 0. So what we need to do is first take the Laplace transformation for the given dE, and next try to substitute the given initial condition into that. Then simplify the complete expression. Make sure that the LHS we have the term y of s and the remaining terms in the RHS. Once you get into this step, then apply the inverse Laplace transformation formula, which basically gives you the required form. So when applying the inverse Laplace transformation formula, the last step, we may have to apply any one of the methods which you have studied in inverse Laplace transformation, like simplifying by using partial fraction method, or by convolution method, or by shifting form, or depending on the problem what we have the function y of s, we may have to go by any one of the known method which we discussed in the inverse Laplace transform. Let me consider an example. We have a second order differential equation problem here. Say y double dash plus 5y dash plus 6y equals to RHS term is 5e power 2t. And the given conditions, when t equals to 0, y value is 2, and when t equals to 0, first order derivative y dash value is 1. So first let me take the Laplace transformation for the given differential equation. So if I apply Laplace transformation of y double dash plus 5y dash plus 6y equals to 5e power 2t. Individually apply this operator. This is Laplace of y double dash plus 5 times of Laplace of y dash plus 6 times of Laplace of y of t equals to RHS. Also we need to apply the Laplace operator. So Laplace of e power 2t. As we know from the previous formulas, if you look at this second derivative Laplace transformation formula, which is s square y of s minus s into y of 0 minus y dash of 0. And similarly, the first order derivative formula, which is s into y of s minus y of 0. So by substituting those two formulas, I will be substituting the second order derivative Laplace formula, which is s square into y of s minus s into y of 0 minus y dash of 0. This is Laplace transformation of second order derivative form. Similarly, Laplace transformation of first order derivative formula, if I substitute, which goes like s into y of s minus y of 0. And I am using the notation for time domain t and the frequency domain s. So Laplace transformation of y of t, I will write it as y of s. So this is basically y of t. Okay. And we know by Laplace transformation of e power et formula, which is 1 by s minus a, so I can write this Laplace transformation of e power 2t as 1 by s minus 2. So this is what we have after applying the Laplace transform to the given differential equation. Now what are the given conditions we have? Y of 0 equals to 2 and y dash of 0 equals to 1. Let me substitute those. Y of 0 equals to 1 is put y of 0 equals to 1, y of 0 equals to 2, and y dash of 0 equals to 1. By substituting this, I will get s square into y of s minus 2 times s minus 1, and in this s into y of s, y of 0 is 2 minus 2 plus 6 times y of s. RHS is 5 divided by s minus 2. Now let me simplify further. by keeping all these y of s terms as uh, in LHS part, that is, keep this s square into y of s, 5 times s into y of s, 6 times y of s in LHS, and try to move the remaining term to the RHS. So if I simplify this, keeping that in mind, s square plus 5 times s plus 6 times into y of s, and remaining terms, if you see, minus 2s minus 1 plus 5 times minus 2, which is minus 10, equals to 5 divided by s minus 2. So these terms will come to the RHS part. So this becomes s square plus 5s plus 6 into y of s equals to 5 divided by s minus 2 plus 2s plus 11. Now let me move this s square plus 5s plus 6 to RHS, which is multiplied by y of s. So this becomes now 5 divided by s minus 2 into s square plus 5s plus 6 plus 2s plus 11 divided by s square plus 5s plus 6. So now we have an expression y of s in terms of the frequency variable, in terms of frequency variable s. This is the first part. After simplifying the given dE with the Laplace transformation formulas. Now what we have to do to get a dependent variable in the differential equation, that is y of t, I have to apply inverse Laplace transform for this expression y of s. Okay, so to apply inverse Laplace transform for this, let me apply L inverse to y of s is equals to 5 divided by s minus 2 into s square plus 5s plus 6 plus 2s plus 11 by s square plus 5s plus 6. Now we have already discussed how to find the inverse Laplace transform by partial fraction method, by convolution method, in some cases by shifting rule also. Now we have two components here. If I take L inverse to these two components, L inverse of 5 divided by s minus 2 into s square plus 5s plus 6 plus L inverse of 2s plus 11 by s square plus 5s plus 6. Let me do it separately. First I will consider this first component, which is 5 by s minus 2, s square plus 2s plus 6. You can write this s square plus 2s plus 6 by factoring. It will be s plus 2 into s plus 3. So compute L inverse of 5 divided by s minus 2 into s square plus 5s plus 6. First we will find out the inverse for this. Next we will move to the second component. So let me write it as, consider 5 by s minus 2 into s square plus 5s plus 6. You can write this as 5 divided by factorizing the second quadratic expression, we will get s plus 2 into s plus 3. Now resolving into partial fractions, this becomes a by s minus 2, b by s plus 2, and c by s plus 3. If we simplify this term, taking LCM of these three terms, three factors, I'll get 5 equals to a times s plus 2 into s plus 3, b times s minus 2 into s plus 3, c times s minus 2 into s plus 2. Now try to compute this constant capital ABC values by substituting s values as plus 2, minus 2 and minus 3. If I substitute s is equals to 2, in LHS we don't have any variable s, so LHS is same 5. RHS, look at this, when you take s is equals to 2, this b component becomes 0 and c component, this also becomes 0. Only the first one we have a times s plus 2 into s plus 3. So this will be, when you substitute s is equals to 2, 4 and 5, 20 times a, so that a value is 5 by 20, simplify further, which is 1 by 4. Similarly, when you try to substitute s is equals to minus 2, the first, that is a term, and this c terms become 0, you will get minus 4 and 1, minus 4b, okay, minus 4b, so that b is equals to minus 5 by 4. Similarly, when you substitute s is equals to minus 3, this b term becomes 0 and this a term becomes 0, only c terms is left. When you substitute s is equals to minus 3, minus 3 minus 2, minus 3 plus 2, if I simplify, that becomes 5c. So c is equals to 1. So we have all three values a, b, c. Now let me substitute into the term. Hence we have this 5 by s minus 2 into s plus 2 into s plus 3, whatever we have written, this will be now that is a by s minus 2 plus b by s plus 2, c by s plus 3. We got a value as 1 by 4, so 1 by 4 divided by s minus 2, and b value we got it as minus 5 by 4, minus 5 by 4 or plus 5 by 4, yes, minus 5 by 4, and c value we have 1, so 1 by s plus 3. So now try to apply inverse at this stage, taking L inverse. L inverse of 5 by s minus 2 into s plus 2 into s plus 3 equals to 1 by 4 times L inverse of 1 by s minus 2 minus 5 by 4 times of L inverse of 1 by s plus 2 plus L inverse of 1 by s plus 3. We know one formula, that is L inverse of 1 by s minus a is e power at, and L inverse of 1 by s plus a is e power minus at. So by applying that, using L inverse of 1 by s plus s minus a equals to e power at, and L inverse of 1 by s plus a is equals to e power minus at. Here in this case a value is 2, so this becomes e power 2t minus 5 by 4 times e power minus 2t plus L inverse of 1 by s plus 3, which is e power minus 3t. This is what y of t for the first component. We have two components, only the first one we have done. Similarly, you have to consider the second component, which is, I think, 2s plus 11 divided by something here. 2s plus 11 divided by s square plus 5s plus 6. So let me consider that. Computing L inverse of 2s plus 11 by s square plus 5s plus 6. Okay. If you want, you can use the shifting form or use the same partial fraction in this case. If I consider the partial fraction for this problem, partial fraction. We have the function 2s plus 11 by s square plus 5s plus 6. I am writing it as s plus 2 into s plus 3. That I can write it as a by s plus 2 and b by s plus 3. Following the same partial fraction procedure and simplifying the terms, we'll get a as 7 and b as minus 5. That means 2s plus 11 by s plus 2 into s plus 3. I can write it as 7 by s plus 2 minus 5 by s plus 3. Now just apply inverse for this. Then inverse of 2s plus 11 by s plus 2 into s plus 3 equals to 7 times inverse of 1 by s plus 2 minus 5 times inverse of 1 by s plus 3. Just use L inverse of e power 1 by s plus a formula. This becomes e power minus 2t and this becomes e power minus 3t. This is inverse Laplace of the second component, that is 2s plus 11 by s square plus 5s plus 6. So now to get the solution for the original equation, look at this equation, original equation what we have in y of s expression. Combine these two results, equation 2 and equation 3 results, that will give you the final answer. Hence, let me take it. Hence, y of t equals to, previous result we have 1 by 4 e power 2t minus 5 by 4 e power minus 2t plus e power minus 3t. This is the first component inverse, and the second component we have 7 e power minus 2t minus 5 e power minus 3t. This is from equation 2 and this is from equation